All right, guys. So these next couple videos that I'm going to post are I want to go through last year's, so this past May, the AP exam, just the free response portion, and I want to just go through the whole test. So a lot of the stuff you're not going to know if you're watching this video now over the summer or at the beginning of school. You're not going to know a lot of the stuff yet because we haven't had class or haven't gotten to it yet. But I just want to take you through an entire pre-response exam, show you kind of what you're up against next year, okay, what you're getting yourself into, and what where you need to be next May when you have your AP Chemistry exam. And I want you to I want to show you how the test marries up to the visible learning document, the visible learning objectives. I'm just going to go through question by question, so it's probably going to be it might end up being 5 videos or so, because I'm going to go one question at a time. And questions 1 through 3 will probably take one video for each one, because they're longer questions, and then the last 4 through 7 questions, they're going to be shorter, so I might be able to do 2 or more questions in one video. But anyway, so what I want to do is just kind of explain to you how the AP Chemistry exam looks, and then actually show you last year's free response. So if you know anyone who took AP Chemistry last school year and had the AP exam this past May, this is the test that they took, to get their AP score. This is the free response portion of the test. So what I'm going to do in this video is I'm going to go through question 1 and show you the different visible learning objectives that you would need to know to answer each question. And I'm going to do that for the rest of the questions too, and just post them here throughout the summer. And hopefully you find it informative as you're gearing up for AP Chemistry. Okay. So let me first go to this sheet. Okay. So just for your information, if you didn't know about the AP Chemistry exam, it's a long test. You got a 90-minute multiple choice section, and you got a 105-minute free response section. So you do the multiple choice first, and on this portion, you have 60 questions to answer in 90 minutes, but you do not get a calculator. And there's, not every question involves a calculation, but, some of them will, and you're going to have to do those calculations in your head. They give you numbers that should be kind of non-calculator friendly, but it's still, it's still some mental math that you're probably going to have to go back and review how to do. And then after the multiple choice, you get a 105-minute free response section. There's 7 questions. Now you might say, 7 questions? Why do I get 105 minutes? Okay. When we say question 1, notice that question 1 is 1A, 1B, 1C, 1D, 1E, 1F, 1G, and 1H. So all these are question 1. When we say 7 questions, we really mean a lot of questions there, right? So really what it is if you look at it, questions 1 through 3 on the free response section are 10 points apiece, and questions 4 through 7 are 4 points apiece. So that's a total of 46 points. So really what you should think about the free response is the free response section is going to be around 46 prompts, 46 things you're going to have to answer, basically. 1 point per thing. There's a handful of questions that might be worth 2 points. So it might not be exactly 46 prompts, but it tends to be close to it. So 46 things that you have to answer correctly if you get, and you're trying to get, as many as you can. They tell you to spend about 20 minutes for each of these questions, 1 through 3, but only spend 6 to 10 minutes depending on 4 through 7, because they're only worth 4 points apiece anyway. So that's kind of how it's set up. All right. Another thing that, as we get closer to our AP exam and you start reviewing, I'll share with you this. But this is kind of, so the way I structure our units in AP Chemistry is kind of different than the way a College Board does. College Board has it separated into 9 different units. And I only have it in 7 units. And what I would say is, if we go down here, the majority of the test is Unit 1, Unit 3, Unit 5, and Unit 6. These are our units. So when you look at College Board's Unit 1, it's not going to match up to our Unit 1. Basically, our Unit 1 is College Board's Units 1 through 4, essentially. So anyway, and so as we go through the test, as we go through the questions, you're going to notice there's a lot of visible learning objectives from Unit 1 and a lot of visible learning objectives from Unit 5 and a lot from Unit 3, because those are kind of the real important units that get hammered on the AP exam. And we'll, explore this document later as we start to review for the AP exam down the road as we get closer to next May. But I just kind of want to show you this, and it's not going to be a surprise to you when you see that question 1 has 3 questions, three things from Unit 1's VLOs, 2 from Unit 2 VLOs, 2 from Unit 3 VLOs, and 4 from Unit 5 VLOs. So, those are going to be the ones that stand out the most, but it's not, everything. But you're going to notice a lot of VLOs from Unit 5 and a lot of VLOs from Unit 1 and possibly Unit 3. All right, so let's dive into it. So let me show you the test. And I'm also going to go through the answers as we do this. I'm going to show you the VLOs that you need to know and how you can find those. But also, I'm going to show you the answers. Some of you might understand it from Chemistry 1. Some of you might not have any idea. Don't worry about it. We're going to cover all this material. This is just me getting it. So let's go. So this is, again, just the free response. So we go to question 1. Gives us a lot of information here. 1A. Okay, so it gives us a 0.3 gram sample of this compound, and it reacts with a strong base to produce this compound, and they're saying if 0.3 grams of that compound react, and they give us our molar mass, it's a they tell us it's a 1-to-1 mole ratio. So for every 1 mole of this compound that reacts, 1 mole of this compound is produced. And they want to know if 0.3 grams of this compound react, how many grams of this compound will be produced. So this is just stoichiometry. So I broke it down here on this document. So question 1, part A, really has 3 VLOs in mind. And notice 2 of them are the same one, right? So it says 2-25A, 2-3, and 2-25A again, all right? So this is what we need to know for question 1. So let's go find those on our visible learning document. So we're in Unit 2. So what was it, 2-25A? So if we go to Unit 2, 2-25A, I can do the following mole conversions: moles to grams or reverse, so that means grams to moles. Okay, and then 2-3 is stoichiometry. So basically, you're following your stoichiometry, you're using your mole ratio, and they told us the mole ratio was a 1-to-1 ratio. Okay, so let's see the answer. All right, so if we go here, we would take our 0.3 grams of this compound. No need to calculate the molar mass, because they gave it to us. So a lot of times you'll see that on the AP exam. They're not going to waste your time with calculating molar mass. That's an easy thing to do. If you know the formula, you just go, okay, 8 times carbon's molar mass plus 8 times hydrogen's molar mass plus 3 times oxygen's molar mass, and you add them all up. Okay, but they don't want you to waste your time with that, because that's just simple math that we all should know how to do at this point. So it's really just, hey, here's the molar mass. Know what to do with it. So we would take our 3 grams, and divided by the molar mass to get moles. Our mole ratio is 1 to 1, 1 mole of this for every 1 mole of that. And then we would do the 2-25A again, which is, oops, 2-5A again. So, whoops, I don't want to do that. I don't want to do that. Moles to grams, or reverse, and now we're doing the moles to grams part. We did the reverse. We did grams to moles here, and now we're doing moles to grams here. But we have a new molar mass, and they gave it to us again, so all we have to do is this divided by that times that, boom, we got 0.272 grams. I wouldn't worry. You don't have to worry so much about significant figures, kind of how we did in Chemistry 1. They would, if they were going to be, like if somebody put 0.27 grams, they would get full credit. Really, it's just showing your work. That's what they want to show, like some kind of setup like this. Now, again, it doesn't have to be T-charts like I do. It doesn't have to be dimensional analysis. You can just say, you just need to kind of show mathematically what you're doing. I think this is the most efficient way to do it, the way I'm kind of showing it here. But just kind of show what you did. And if you put 0.3 grams, you'd probably get full credit. Sometimes within the question, they might say, make sure your answer has the correct number of sig digs. And if they put that here in this specific question, then you would have to have 0.272 grams. And it would probably be 1 point for the correct setup and then 1 point for the correct number of significant figures. So that might be a 2-point question if that were a prompt here, but it's not. So it's not something that you really have to worry about. All right, so question 1A, all from Unit 2, stoichiometry and mole calculations, okay? 1B, so let me go back to the blank test. All right, so as part of the experimental procedure to purify this compound's crystals, after the reaction is complete, the crystals are filtered from the reaction mixture, rinsed with distilled water, and dried. Some physical properties of this are given in the following table, okay? So they give us physical properties. It says the student's experiment results in 87% yield of the compound. The student suggests that some of the H crystals dissolved in the distilled water during the rinsing step. Is the student's claim consistent with the calculated percent yield justify? So let's look at what VLOs these cover. So here's, it's Unit 1, okay? It's Unit 1, and so 1-5-6A, but it's also a lab VLO. So I'll show you where the lab ones are. So this is lab-3, L-3, and it's 1A. So we'll see what that's about. So again, so let's go to Unit 1 first, and then I'll take you to the lab VLOs. So Unit 1, and it was 1-5A. Or what, let me just make sure. Oops. 1-5-6A, sorry, 1-5-6A. So 1-5-6A, I understand the rule like dissolves like, and can use polarity and IMFs to make predictions about solubility, okay? And then it was also L-3, so if you go past all the units, so we have 7 units, then you get to your laboratory techniques, and these are things we kind of do sprinkle in throughout the year during all the different units. And it was L-3 separation techniques, so we're talking about filtration. So it's really just understanding the filtration process. Okay. So this compound is polar, and you know it's polar because any organic compound that has more than just carbon and hydrogen, if it has oxygen or anything else, it's going to be polar if it has any other type of functional group. So it's polar. It probably has hydrogen bonding, but because it's polar, it would be expected to be water soluble. So rinsing it with distilled water would make some crystals possibly dissolved with that distilled water. And so you would have less of your dry crystals, and that would and give you, less than 100% yield. So, whoops. So the answer, yes, if some of the crystals dissolved and ended up in the filtrate, less solid would be measured, resulting in a lower percent yield. Okay, so there you go. All right, let's go to question C. Given the physical properties in the table, so we got the melting point, we got solubility in water, so it tells us it is water soluble, 2.2 grams per liter. Specific heat capacity and heat of fusion. So instead of using like dissolves like and knowing that this is polar, you could say, yes, it's slightly water soluble here. So you could use that physical property there. That goes back to part B. So part C, calculate the quantity of heat that must be absorbed to increase the temperature of this many grams of the compound. They give you the molar mass again, so you don't have to worry about calculating it. From 25 degrees Celsius to the melting point, and also melting the crystals completely. Okay, so this is going to be from Unit 3, heat calculations. So let's look at what VLOs Part C is covering. Okay, whoops. So C is 3-4, 3 and 3-3, 7. So let's see what those are all about. So 3-4 and 3-3. So 3-4 is calorimetry, but 3-4-3 is Q equals MCAT, so Q equals MCAT calculation. And then it was 3-3, 3-3-7, which is I can calculate energy required for a phase change using delta H of fusion or delta H vaporization. So delta H of fusion is for melting and freezing, and delta H of vaporization is for vaporizing and condensing. So let's look at the answers here. So the deal is, I didn't sketch a heating curve on my answer key, but understand what we have to do. The first thing we have to do is we're starting at 25 degrees Celsius. We have to heat the solid up to its melting point. So we got to do Q equals MCAT to go from 25 degrees Celsius to 159 degrees Celsius. But then we have to use the molar heat of fusion, which they give us right here, the heat of fusion, to go from the solid, it all as a solid at the melting point, to all of it as a solid liquid at the melting point. So we have to, if you can envision a heating curve, that kind of staircase diagram, we're here, we got to heat it up to the melting point, and then we got to go across that first plateau to completely melt it. So that's two calculations we need to do. So the first one would be Q equals MCAT. So we had our mass, they gave us our specific heat capacity, and our temperature change, or delta T, would be 159 minus 25. So we have to, this is how much energy is required to heat it up to the melting point. And then we have to use the molar heat of fusion. They give us energy per mole here to calculate how much energy is required to completely melt it. So we'd have to convert to moles. They gave us the molar mass. Then use the molar heat of fusion, but understand that this was joules. Notice the heat capacity was joules, but the heat of fusion was kilojoules. So when we add the energies together, they either all have to be joules, like I have here, or they'd all have to be kilojoules. So we got 16.5 joules for the first part. And then when we do this calculation, I converted from kilojoules to joules here, and we got 20.6 to melt it. So all we have to do is add those two numbers up, and we get our total energy there for part C. I'm guessing this is a 2-point question, knowing how to do this and knowing how to do that. So I don't know how they would work it out, but yeah. So anyway, that's part C. So if we go to part D, okay, so they give us the structures, okay, and what the thing to notice is, notice that this has a -9 degrees Celsius melting point. This has 159 degree. So this acid has a much higher melting point than this. And really the question is why? And it's, remember, anytime you have differences in melting point, differences in boiling point, it's about intermolecular forces. So this compound must have stronger IMFs than this. But if you read the prompt here, it says it says both of these compounds have London dispersion forces, dipole-dipole interactions, and hydrogen bonding. Okay, but we want to, so this has hydrogen bonding, this has hydrogen bonding, this has dipole-dipole, this is dipole-dipole, this has London dispersion, this has London dispersion. But why does this have such a higher melting point than that? Okay, so remember, when you're talking about covalent compounds, organic compounds, when you're talking about IMFs, hydrogen bonding is pretty much the top dog. So the question is, why does this have stronger hydrogen bonding than that? And what you'll notice is this only has one place where you can have hydrogen bonding, right? That has one Fon bond. If you were one of my students, you'd know what a Fon bond is, but it has one of the special bonds for hydrogen bonding. But notice this has two. This has two sites for hydrogen bonding. This, you have a Fon bond here and you have a Fon bond here. Okay, so they're both polar, so they both have dipole-dipole interactions. They both have Fon bonds, right? So they both have hydrogen bonding, but this has more Fon bonds. So more possible hydrogen bonding, so it takes more energy to separate. Okay, so anyway, let's find out what VLOs that is. Whoops. So 1-5 8 and 1-5 9A. Now, it says kind of 1-5 9A because you don't need to know 1-5 9A to answer this question, but it kind of helps you if you're really familiar with it. You wouldn't even have to read the prompt that well. You should be able to look. Whoops. You should be able to look at this compound and say, okay, it's polar, and it has a Fon bond, so this has all three. They shouldn't have to tell you this experiences all three and this experiences all three. You should be able to look at the functional groups here and know that, okay, this has hydrogen bonding, dipole-dipole, and London dispersion. And this also has hydrogen bonding, dipole-dipole, and London dispersion. Okay? So you should be able to look at that and see that. So if you look at the VLOs, here, it's 1-5. We're in intermolecular forces again. So 1-5 8, this is the main one. Understanding why something has a higher melting point than another thing, using IMFs to explain it. But 1-9A, I can recognize functional groups that result in hydrogen bonding, and B, I can recognize functional groups that result in dipole-dipole. So the reason why this is kind of important is they could have been a little bit, they might have asked you, in previous tests, I've seen them give you a list of compounds and you have to, or give you compounds and you have to list the IMFs that they have. They could have asked you which IMFs do these experience. And the answer, again, they gave it to you, is all three. But you should be able to look at this and know it's all three, and you should be able to look at this and know it's all three. So that's why I said kind of 1-5 9A and B. But anyway, so the answer, again, this has two sites for hydrogen bonding. This only has one. So let's go to my explanation. The salicylic acid has two OH bonds in the molecule, where the methyl salicylate has one. This allows for more possible hydrogen bonding between molecules. There you go. Okay. And then let's go to, so they give us a titration curve, and so let's go to E. Okay. So the rest of the questions here, are all from Unit 5, and they're all basically Unit 5 titration questions. There might be a couple that are a little bit different, but 5-4 is titration. So anyway, let's read the question. So it says 20 milliliters of 0.01 molar. The acid is titrated with 0.02 NaOH. They made a titration curve, and then they ask you, using the information in the graph, estimate the pKa of the acid. So using this, figure out the pKa. And so if we look at the VLOs, 5-4 5A is the VLO for this. And so let's find that on our visible learning document. 5-4 5A. I can determine the pKa of an acid or a pKb of a base using this point, and this point is called the half equivalence point. So I can use the titration curve to find, I should say find, I'll change that now, the half equivalence point, and it says I can determine the pKa of an acid. So boom, that's what the question's asking. So let's do it. So what you do is the equivalence point is at the point of inflection, so somewhere around here. So the volume at the equivalence point is 10 milliliters. The half equivalence point is half that. So if the volume of NaOH added is 10 milliliters at the equivalence point, half of that, 5, is the half equivalence point, and the pH at the half equivalence point is equal to the pKa. So at 5, the pH is around 3. So the pKa is 3. There you go. All right. Let's do F. When the pH of the titration mixture is 4, is there higher concentration of weak acid or its conjugate base? So 4, notice that we're beyond the half equivalence point. So this is going to be VLO, VLO 5-4 7. And it really, specifically, it's during the buffer region. So it's 5-4 7B, understanding the titration curve during the buffer zone. And if we go back to the diagram, between this, after you start the titration, so slightly after 0, but before the equivalence point, so in this case, right before 10, this region right here is called the buffer region. And the half equivalence point is the midpoint of the buffer region. Anything before the half equivalence point, you have more of the acid and less of the conjugate base. Anything after, you have more of the conjugate base and less of the acid. Okay, so we have more of the conjugate base. Okay, so that the concentration of that is higher. As the titration occurs, you have the OH minus from the sodium hydroxide that you're adding reacting with that. So this becomes that as the titration occurs. We're beyond the half equivalence point, so the conjugate base, A minus, is greater in concentration than the weak acid. So HA is a generic term we give for a weak acid, and A minus is a generic term we give for a conjugate base of a weak acid. And so at that point, we know this concentration is greater than that concentration. Okay. So let's go to G. The student researches benzoic acid and finds that it has similar properties to salicylic acid. They give us the Ka for benzoic acid, and they ask us to calculate the pKa of benzoic acid. So that's really easy. And again, let's go to the VLOs. G, 5-39. So let's go to 5-39. 5-39. I know that pKa equals the negative log of the Ka. All right. So basically, in acid-base chemistry, anytime you see P in front of something, it just means take the negative log of that. So all we have to do is negative log of the Ka, which was this number, negative log of that number, log base 10, and we get 4.20. Okay, so 4.2, 4.20, that is the pKa. There we go. So notice that the pKa of benzoic acid is higher than the pKa of the salicylic acid, okay? Which means benzoic acid is a weaker acid than salicylic acid, okay? The higher the Ka, or the higher the pKa, the weaker the acid. So, the higher the Ka, the stronger the acid, but the higher the pKa, the weaker the acid. All right, so it says the student performs the same titration with benzoic acid instead of the salicylic acid, but they're still using the same amount of NaOH. And we have to sketch that curve. The pH of the benzoic acid is initially 3.11. So we go to 3.11, okay? We know that the half equivalence point is where pH equals pKa, so that's 4.2. So at the half equivalence point, it would be 4.2. And we know the half equivalence point is going to be the same because we're starting with the same amounts. And so we started with the same amount of the acid, and we use the same amount of the base, meaning concentration, 0.01 molar benzoic acid, 0.02 molar NaOH. So that's not going to change. So we know where 4.2 is. The equivalence point is going to be at the same volume here. It's just going to be a little bit higher. And then as we go, it's going to be a little bit more basic at the end. All right. And we're going to learn all about this when we get to Unit 5. But essentially, this is 5-4-7. It's basically the whole thing. Understanding what a titration curve is going to look like the entire way through a titration with varying acid strengths, various base strengths, that kind of thing. All right, guys, so that was question 1, and that was all the VLOs that were question 1. So just kind of showing you how the visible learning document might help you. But really, the visible learning document doesn't have everything there, right? You have to know this, but knowing what a titration curve looks like throughout a titration, knowing what an acid-base titration curve looks like throughout a titration, me saying that and actually knowing it are different things, right? You have to spend time to know it. But I just kind of want to show you how it works. So that's question 1. I'll have another video maybe tomorrow or as we work through this for question 2, question 3, and then we'll end up pushing. I'll try to go through the whole test in the next few days and post it in our Schoology site for summer assignments. All right. So anyway, hopefully you find this informative. Not, what are you gonna do?